Namaskar friends, welcome to the last session of 7th week, that is on hole making. So let us just have a brief review of the 7th week, that what we have discussed. We have tried to discuss the various joining methodologies, joining strategies that can be used for joining of plastics, and we have already finished 4 sessions in that. That is session number 31, 32, 33 and 34. So what we have discussed? We have discussed the induction welding of plastics, we have discussed the ultrasonic welding of plastics, we have discussed the vibration as well as spin welding of plastics, we have also discussed the microwave heating mechanism or the use of microwave energy for joining of plastics. So basically, why joining has become necessary during the product design, that also we were able to highlight in the very first session, that was session number 31. We have seen that it is difficult to make larger products using the conventional processing techniques like injection molding or compression molding, and therefore we design the product in such a way that the product is manufactured in simpler parts and then these simpler parts are assembled together using any one of the joining strategy. And if we refer back even to week 6, in week 6 also we discussed or we reviewed the various joining strategies, where we have seen that adhesive bonding is one technique, we have seen welding, we have seen brazing, we have seen soldering, we have seen mechanical fastening, we have seen riveting. So all these techniques are used for the assembly of the simpler parts into the final product. Today, as you can see on your screen, the target is hole making. Now why holes are required? Now you can see in the various joining methodologies that we have seen, when you go for ultrasonic joining or you go for vibration assisted joining, in those cases we have made flat surfaces only, but those are not the only type of joints that we usually make in case of products. In products, different types of joints will be there. Many times the surfaces that are to be joined together will be aligned at an angle, or there may be another specific requirements where the induction welding or the vibration welding or the ultrasonic welding may not be suitable. So there, in that case, what is required? We require to make holes in the parts so that the mechanical fastening can be facilitated or the riveting can be facilitated. So for those situations where the other standard joining techniques such as adhesive joining, vibration joining or vibration welding, ultrasonic welding, induction welding, these processes are not suitable, in those cases we will go for mechanical fastening or riveting with the help of threaded screws, and in those cases we require a hole in the product that we are making or the parts of the product that have to be assembled together, and then these parts have to be designed accordingly, where the holes must be located, what must be the center to center distance between the hole, what must be the diameter of the hole in context of the thickness of the sheet that we are making. So all those things have to be kept in mind when we are designing the product, which is going to have different parts which are going to be joined using the mechanical fastening technique, using the threaded fasteners. So that is basically the purpose of this lecture, where we are trying to understand that how hole making must be accomplished in metals as well as in non-metals. So whatever examples we have taken, some of them may be relevant for thermoplastics, some of them may be relevant for the metals. Now let us start our discussion and try to understand that importance of hole making during the product design stage. Now during the initial introduction that we have already established the importance of hole making and the overall summary of this week, because today is the last session for this week, that is week number 7. So why week number 7 has been designed, I have been able to highlight that whenever the complex geometries of the products have to be processed, the joining becomes inevitable, and for joining different techniques have to be developed depending upon the raw material, depending upon the material with which the product is going to be made, and based on that Hole making also is one of the important strategies which will facilitate the mechanical fastening of parts. So that is the overall summary of this week, and the last topic is hole making. Now holes can be added to a part for functionality or to reduce the overall part weight. Now two things are there, these are additional things. Whatever I have told in the introductory part, that states or that establishes the importance of hole making only for fastening purposes, but sometimes we may create holes in the product to make it lightweight also, as we can see it is mentioned here. Sometimes the holes may be required in the part to reduce the weight of the part. Also holes can be added to a part for functionality. So some function these holes will provide. Sometimes we may require holes for maybe pushing in water, or maybe for as a coolant we need to push water or some other oil into the part or the product. So in that case also holes may become inevitable, or the holes may be used for that purpose. So depending upon the requirement we will make the holes in the product, and most importantly the holes are made for fastening purposes. Now how the holes can be made? Core pins. Now core is an important word which we usually associate with the sand casting process, and all of you know why the cores are used. So core pins are typically used to form a hole. So if you remember, in case of sand casting also cores are used. So very quickly, maybe if I can draw a diagram of a mold cavity, and if we want to require a hole here, we will place a core like this, and we will have the core prints here. So this is basically a core which is placed inside the mold cavity in sand casting to produce the, and this is the place which will be filled by the metal. So we will have a core inside in order to have a through hole inside the casting. So similarly we can place a core here also and produce this hole. Similarly a core can be placed here and this hole can be produced. So core pins are typically used to form a hole, preventing the molten plastic from filling in that space. Now suppose at this place if we have placed a core maybe of this much size, it will not allow the molten plastic to fill this area because this is already filled with core. So molten plastic will flow around and fill the other area, and we will get a hole here in the plastic after the solidification process. So through holes go all the way. This is example of a through hole. Through holes go all the way through the part. Blind holes do not completely go through a part. Just a classification. This is a through hole and this is a blind hole because it is not going all through the part. So different types of holes can be made. Here we are taking an example of a plastic material. We can create a through hole in a plastic with the help of a core pin, or we can make a blind hole in a plastic product using the core pin. Now core pins for a blind hole are only supported by one end. So here we can see, if we go back to the previous slide, this type of core pin can be supported on both sides, whereas this core pin can only be supported on one side. So therefore we can see that core pins for blind hole are only supported by one side. So here also again the diagram can be made. This is the hole that we want to create. So this is a blind hole. So the core pin will only be supported on this side. There is no support to the core pin on this side, supported by one end. So there is a greater degree of difficulty in forming them without the defect. So there are chances that this core pin may get deflected in one of the directions and we may not be able to produce a good quality hole. So forming holes can lead to defects or have a negative impact on the aesthetics. So we may not be able to produce good quality holes in plastics using the core pins. Since the molten plastic flows around the core pin, it can leave a weld line which may be visible and or be weaker than the remainder of the part. So this is clearly highlighting that hole making in plastics is a challenging task. Why? Because of the defects that may be produced. So we have to be careful and we have to see that how we can make a good quality hole in a plastic part using the standard approaches. So if we are not able to use the standard approach such as the use of a core pin, we may have to go for the advanced techniques for making holes in the plastic parts. Now, what are the design guidelines for hole making? We have tried to understand that what are the techniques. We are just one technique we have been able to review, that is placing a core inside the mold so that the molten plastic will fill all the area except where the core pin is placed, and when you take out the core pin it will create a hole after the solidification of the plastic. So you will take out the core pin after the molten plastic has already solidified, so it will create a cavity which will be a hole. The hole can be a through hole or it can be a blind hole. Now what are the things or guidelines that we must keep in mind when we are making holes either in plastics or in metals? So let us see now. One of the important thing is the distance between the holes. Now this is our first hole, this is our second hole. What must be the distance? So this distance is clearly marked here. What must this distance be? Now this distance is clearly mentioned in the sentence here. Now how that distance we must decide? Distance from the edge of the hole. Now here this is the edge of the hole, this distance, or we can say this distance already marked here. So the distance from the edge of the hole to a vertical surface or edge or part or rib or another hole should be at least 2 times, very important, at least 2 times the thickness of the part, at least 2 times the thickness. So whatever is the thickness, if we say this is our plate in which we want to make the hole, this will certainly have certain thickness. So if we say that this is the thickness of this plate and we mark it by T, so this from the edge of the hole to the vertical surface must be 2 times the thickness, or the distance between the 2 holes must be at least the diameter of the core pin, diameter of the hole, or 2 times the thickness. So whatever is the diameter of the hole, that distance must be there in between, or it must be twice the thickness of the sheet which I have, or the plate which I have already shown, that is 2 times of T. So that is the guideline related to the distance of the hole from the edge and the distance between the 2 holes. This is a very important guideline, specially used for in case of metals. Blind holes should not have a flat bottom. This is example of a blind hole and it is showing a flat bottom here, is not advisable. It must have a bottom surface like this. Why? Because flat bottomed holes cause problems with subsequent operations. A standard twist drill, it is something like this, a standard twist drill, this is a point angle theta. So the standard twist drill creates a hole with a conical bottom. So if this drill goes inside, it will definitely create a hole with a conical bottom. So we must not specify a flat bottomed blind hole in case of our parts where the hole has to be done in the blind manner. Especially in case of blind holes, flat bottoms may not be specified. We can specify a conical bottom, and therefore it is the right way of producing a hole inside a plate or inside a thick plate using the twist drill, where the cone or the bottom is conical in nature, which is corresponding to this geometrical feature of the twist drill. So this is another guideline which must be kept in mind. This is another guideline, third guideline, holes should not intersect a cavity. So this is also very important. Here there is a cavity, here the holes must not intersect a cavity, which is very important. If an intersection is unavoidable, many times this is not, because here the hole is intersecting a cavity, it is not recommended. So if an intersection is unavoidable, at a minimum the center line of the hole should be outside the cavity. So if there is a cavity here, the center line must be outside the cavity. So that must be taken into account. So this is the right way of producing a hole where it is intersecting a cavity. The center line should be, if it is unavoidable, the center line of the hole should be outside the cavity. That must be taken into account. Holes created in the direction of the opening or closing of the mold. Now suppose we are producing a hole in a process called maybe die casting, or in case of metals, or injection molding in case of plastics. Now the two die halves or the mold halves will close to each other. So when they are closing, it is possible to create a hole along the direction of opening and closing. So holes created in the direction of the opening closing of the mold or parallel to the parting line are relatively easy to produce. Suppose this is the opening and closing direction. One will be, of course, I must not show both moving, one will be stationary, another one is moving and closing the mold. So this is the direction of opening and closing of the mold. So it is easy to make a hole in this direction. Or suppose we assume this is my parting line. So the two mold halves are closing like this. So along this direction also it is easier to make the hole along the or parallel to the parting line, are relatively easier to produce. Here also there will be maybe a difference in the relative ease, maybe along this direction it is better or along this direction it is better, but if it is perpendicular direction, this direction and this direction, relatively better as compared to angular holes that may be required in some of the products. So holes created in the direction of the opening closing of the mold or parallel to the parting line are relatively easy to produce, but holes at different angles, which I have already highlighted, holes at different angles can be created but may require special action in the mold utilizing core pulls or cams, which can have significant cost impacts. So special requirements, special requisites are there when angular holes have to be made. We have to maybe design the cams in such a way that we are able to produce a conical hole or maybe an angular hole while making the product. So maybe when we are designing our product, we have to specify a hole for a specific purpose. We must take into account the difficulties encountered in producing the angular holes in the product. Always we must try to specify the holes in the direction that is either opening or closing of the mold or maybe along the parting line, because those are easier to produce. Angular holes are difficult to produce, require special requirements or special equipment or special tools, and therefore must be avoided. Now let us take a case study of hole making. Now we know there are other guidelines also related to hole making, but we have to make a comprehensive case that what are the important things that we must keep in mind when we are doing the operation of hole making in different types of materials. Now this is a case study related to hole making in a special class of materials which we have already discussed during our week second, that is engineering materials. In second week our focus was on engineering materials, and we have discussed a special category of materials which are called as the composite materials. So we have seen at least 3 or 4 specific guidelines which must be kept in mind when we are making holes or when we are specifying holes in our product design. And suppose we have to make holes in our product which are being used for assembly purpose or for fastening purpose or for reducing the weight of the part or for any other purpose or for improving the functionality of the part. When holes become inevitable, we can go for specific strategies for making the holes, and here we are going for a specific material which is basically a composite material. Now what are the techniques of hole making in polymer matrix composites? So in polymers we have already seen that if there is a plastic part, we can make a through hole using a core pin. In today's class only we have seen that, or we can make a blind hole where this is also a part of this thing. We can make a blind hole again using a core pin, and there can be certain defects that may take place during making of holes in plastics, or we can say polymers. But when we talk about the polymer matrix composites, in that case there will be fibers also along with the polymer, so which makes the process even more difficult. Also in polymer matrix composites, many times we make them in the form of layers also. So let us take an example. So this is a layered composite. We are seeing only one view of this. This can maybe go in this direction also, like this. Suppose now we want to make a hole in this laminate. So once the material is drilled, there are chances that the layers that are there in the composite may try to peel up like this when the drill is rotating also and it is going down also. So there are chances of layers getting peeled up here, that is called peel up type of delamination, and subsequently these are the layers of the fibers which are reinforcing the plastic or the polymer which is already. So this is a polymer matrix composite. So again you can see the drill is making a hole, it is going down, it is rotating also. So when it goes down, suppose it reaches this point, there are chances that the bottom layers may open up. This is again a form of delamination when the drill is just at the exit. So this type of delamination is called the push down type of delamination. So we can have a peel up type of delamination, we can have a push down type of delamination, and especially even if we are making a hole in a aluminum plate also, there are chances of formation of different types of burrs. So burr formation is also an issue in metals. Similarly in polymers and polymer composite, there are chances of delamination. In polymers we can call it as burr. In case of polymer matrix composites where we have layers of fibers, there are chances of push down type of delamination. So I will write the word because it is a very common word which is used in case of polymer matrix composites, delamination. So at the entry of the drill inside the composite, when you are trying to make a hole, you will have a peel up type of delamination at the entry, and at the exit you will have a push down type of delamination. So both are dangerous, both have to be avoided, and there are data available where 60% is the rejection rate for the composites. So when you make holes, 60% of the holes are rejected. Why? Because either the push down type of delamination takes place or the peel up type of delamination will take place, and the hole quality will be very poor. So the fibers will also come out. Sometimes we call it a fiber pull out. Sometimes a lot of heat is generated, matrix burning, because matrix is a polymer in this case. So as the name suggests, polymer matrix composite. So polymer is a matrix, so polymer may burn at very high temperature, at very high speed and feed rate. So lot of problems are there when you try to make a hole in a composite material. And these days composites are being used not only in aircraft industry, they are being used in automotive industry also, they are being used in sports industry also, they are being used in marine industry also. So therefore when we are proposing the use of a polymer matrix composite or a fiber reinforced plastic in any product, we need to understand that if a hole has to be made in this product or part, what are the difficulties that we may encounter during the hole making. So all these things whatever I have explained are very serious issues and have to be taken into account. But the picture is not that sad, it is very rosy. Why? Because number of strategies have been developed by the researchers worldwide to mitigate, to minimize the effect of this type of damage that takes place during hole making in the polymer matrix composite parts. Now what are the strategies which have been developed? Some of the strategies are woodpecker cycle. We will see them with the help of a diagram. Use of a backup plate, maybe we can put a backup plate here which will not allow the push down type of delamination to take place. Helical feed method is another method which has been devised. Ultrasonic assisted drilling, as we have seen in this week, only ultrasonic welding process. Similarly, ultrasonic frequency can be used or vibrations can be given to the drill in order to make the drilling forces less, so that lesser damage is produced. So let us quickly see each one of this with the help of a diagram, but the major emphasis of developing all these strategy is to reduce the damage that takes place during hole making in polymer matrix composites, which is a special type of material which is used for aircraft industry, but now it is being used for a lot of other applications also. Now first let us take the example of a woodpecker cycle. The peck drilling simulates the action of a woodpecker bird making a hole in a tree. We will try to understand this with the help of a picture or a diagram. So all of you may have seen a woodpecker, how it makes a hole in a tree. So it goes one step at a time, so maybe step by step it creates a hole. So the peck drilling is the similar action only, developed to overcome the problems of chip removal. So if you do it step by step, chips can be easily evacuated, and consequently the drill damage is also, or drill breakage is also minimized. There are two ways to perform a peck drilling cycle during the drilling in FRP composites. So FRP, another name of polymer matrix composites. So why we do for peck drilling? For better productivity, for better chip evacuation. Now this is the woodpecker cycle. You can see here the drill first goes down, makes a hole till this point, then it comes back, then it again goes down up to this depth. So initially it goes up to this depth, then it goes up to this depth, then again it comes out, then it further goes down the depth, and then it comes out. So we can see the hole, this is the total depth of the hole which has been produced, but it has been produced in the third step. This is step 1, this is step 2, and this is step 3. So we go inside, then we come back again to a next depth level and then come back. After each drilling cycle, retract the drill out from the hole to ensure that no chips are stuck onto the drill. So this is one approach which has been found to be applicable, especially in case of very thick composite parts or very thick composite laminates made by polymer matrix and reinforcing fibers. Now what are the advantages? Well, let us quickly go through the advantages. Better productivity, low drill breakage, better chip evacuation, decrease in the thrust force, decrease in the drilling temperature, decrease in the drilling induced delamination. So you can see all these advantages are associated with the woodpecker drilling cycle. So wherever possible we can go for this type of drilling strategy in making holes in polymer matrix composites. Now this is the use of the backup plate. This is the drill. It is rotating in this direction, it is going down also in this direction, and this is the backup plate. It is already shown in red color. So this backup plate will not allow the delamination, the bottom layers. Now these are the layers in the laminated composite. When the drill will go down, this backing plate will not allow the lower layers to delaminate. Otherwise, if the backup plate is not there, the bottom layers of the fibers will tend to delaminate. So this type of delamination can be easily avoided using this backup plate. Now what are the advantages of this? Advantages of backup plate method are decrease in the drilling induced damage, no push down delamination, as I have explained in the diagram. Quality of the hole produced is very good. So we have seen you can put a backup plate below the laminate. Suppose this is the laminate I want to make hole in, I will put a backup plate just below this and clamp this on the work table and try to make a hole through with the drill. So the bottom layers of the laminate will not tend to open up, so the push down type of delamination can easily be avoided and a good quality hole can be produced. Then there is a helical feed method. A helical feed drilling method improves the drilling performance over the conventional drilling. So conventional drilling, all of you know what is conventional drilling. So helical feed drilling method is better in performance. Now what is a helical feed method? The difference between the two methods is that the drill in the helical feed method moves down helically. In conventional drilling method, your drill will go down in a straight manner, whereas in case of helical feed method, the drill will go down in a helical feed. So, it is not straight, it will go in a helical feed manner with respect to the drilling axis. So, this is the drilling axis as I have shown in the diagram. So, the drill will go down in a helical manner, while the drill in the conventional drilling moves straight down the axis. So, in case of conventional, as I have already highlighted, the drill will go down straight along the axis, but in case of helical feed, it will go down in a helical manner along the axis. So, this is an example. Advantages of helical feed method: chip removal is better, flow of the coolant is better. Most of the time we have to take a decision whether the coolant has to be used or it can be avoided. Thrust force is less, decrease in the drilling induced damage, high quality of hole is produced, temperature produced is less, decrease the matrix burning out problem or matrix burnout problem. So, burnout can be put like this. So, it can avoid the matrix burnout problem also. So, we can see that we can put a plate below the composite laminate, we can use a helical feed method, we can use a woodpecker drilling cycle. So, there are different strategies which have been applied by the researchers worldwide to reduce the effect of delamination, whether it is a push down delamination or it is a peel up type of delamination or it is matrix burning or maybe it is fiber pull out. So, all these problems are associated with polymers which are reinforced with the fibers. So, those type of materials can easily be drilled or the holes can be produced in composite materials which are specifically polymer matrix composite materials using any of these strategies. So, the last strategy basically can be that we can go for the vibration assisted drilling also, where the drill will be doing its action in the normal manner, but the will also be vibrating at a ultrasonic frequency. So, we can go for those kind of drilling strategies also. We can try to optimize the cutting speed, we can try to optimize the feed rate. Also, many researchers have focused on optimization of the drill point geometry. Today I have named only one geometry, which is the twist drill, but there are other very specific geometries like 4-facet drill point, parabolic drill point, 8-facet drill point, jaw drill, step drill, brad and spur drill. There is a long list of drills which have been developed, designed and implemented for making holes in polymer matrix composite. So, I think the time is over for today's session, otherwise we can discuss this topic in much more detail, but the overall objective has been met, that we have to be very cautious while designing our products. Why? Because if the holes are going to be there in the product, the holes may be associated with certain degree of damage, certain degree of defects which may have a detrimental effect on the performance of our product. So, whenever we are designing a product, we must keep in mind the holes that are going to be produced, the process that is going to be used for making the holes, as well as the damage or the defects that may occur during hole making operations, because these are going to affect the performance of our product. So, with this we can conclude the today's session. We will start our discussion for the last week and we will see important topics which are left by now, and we will try to focus on the topics which are going to be relevant really during the product development cycle. Thank you.